When talking about rotating reference frames, we have to address an issue that can come up, that of fictional forces. So fictional forces occur when you incorrectly apply Newton's laws. Now, Newton's laws apply only to inertial reference frames. Inertial reference frames are non-accelerating reference frames. So as long as the reference frame is moving, either not moving or moving at constant velocity, Newton's laws hold. So for example, an elevator that's not moving, if you drop an object, it will fall as you would expect. If an elevator is moving at constant velocity downward or upward, and you drop a ball, it will fall in the same way. It'll fall in the same acceleration, the same thing you would see in a stationary elevator. But if an elevator is accelerating upward or downward, then different things happen. For example, you can imagine an elevator at the top floor of a very tall building. You're about to drop a penny to see how it falls, and someone cuts the elevator cord the instant you let go of that penny. Well, you, the elevator, and the penny all fall at the same rate. But from your perspective, it looks like the penny is just floating there in the air next to you. It's not falling at all. So you get a different result in an accelerating reference frame. So we have to be careful when we apply Newton's laws. We have to look at situations from non-accelerating reference frames, and that includes non-rotating reference frames. Remember, uniform circular motion is caused by a centripetal acceleration. So if you're in a reference frame that's rotating, well, then you are in a non-inertial reference frame, and Newton's laws don't strictly hold. Now, the argument for that is, if you go on in physics, you can reconstruct Newton's laws in rotating reference frames, but what happens is you get terms out called fictional terms or fictional forces. And many of you probably experienced fictional forces, and I'll use a common example. So, what happens if your reference frame is accelerating? What weird things can happen? Well, imagine we're looking down at a car. So this is a car, here's the driver and the passenger in a car. That car was traveling north up in this drawing, but then takes a sharp right turn. Person forgets that their exit's coming up and very quickly turns to the right. What do we feel in the car? Well, if you're the driver and the passenger, you feel like there's a force shoving you to the left, right? The driver feels like they're being pushed into, their left shoulder is being pushed into the door. The person on the right feels that they're being pushed away from their side and into the driver. The faster this turn, or the faster they're going when they make the turn, the bigger the centripetal force needed to accelerate them around the corner, and the bigger that push into the door feels. That push makes it feel like you're being pushed to the outside. You're being pushed to the outside of the curve. So if you turn to the right, you feel you're being pushed to the left. If you turn rapidly to the left, you feel you're being pushed to the right. And this is called a centrifugal force, or centrifugal force. Remember, centripetal force is a center-seeking force. Centrifugal or centrifugal force is a center-fleeing force. So it is going away from the center of motion. Now it's a class of forces, just like centripetal force is. But in this case, it's a fictional force. And why is it a fictional force? Because you are actually not being pushed to the left as you rapidly turn the steering wheel to the right. What is actually happening is your body wants to go in a straight line, right? Objects in motion tend to stay in motion in the direction they're moving unless acted on by an outside force. Your body and the car wants to go straight. The friction from the wheels on the road force you around this corner. So what happens is the wheels are forced around that corner. The force is inward. Well, the wheels are attached to the axle, which is also forced around the corner. The axle is attached to the frame of the car, which is forced around the corner. The frame of the car is attached to the seats, which is forced around the corner. You're sitting in those seats. Friction keeps you in those seats, or a seatbelt, hopefully, keeping you around that corner. So what's really happening is the car, the seat you're in, and even for a rapid change, the door, you might hit the door, it's really the door hitting you. The seat pushing you around the corner, the door pushing you around the corner as you rapidly turn. And because of Newton's third law, for every action there's an equal and opposite reaction, the centripetal force of the door pressing on you, there's a force from you on the door. That's the centrifugal force. But that's the force on the door, not the force on you. A common example of what might happen is imagine you have your sunglasses sitting on the dash. You place your sunglasses on the dashboard and then you rapidly turn the car to the right. What happens to your sunglasses? It looks like there's an invisible force that pushes your sunglasses to the left on your dashboard. Like someone just went and swiped them off to the left. Why? Well, what happened was your sunglasses wanted to go in a straight line. The friction between your sunglasses and the dashboard, which the dashboard might be a slippery vinyl, wasn't enough to force the sunglasses around the corner. So as your car turned around the corner, the sunglasses kept in a straight line and they looked like they went to the left. So you can see this motion more clearly if you look at it from above, from a non-inertial reference frame. You can see what's actually happening. Inside the car, it looks like weird things are going on. That your sunglasses just magically flew off to the left. What pushed them? I didn't see anyone go up there and hit them. And we call that a centrifugal force. And it is a centrifugal force in that it looks like it's an outward moving force, but it's fictional. In truth, there were no forces on your sunglasses. That's why your sunglasses didn't accelerate around the corner. That's why they went in a straight line. So those are called fictional forces, and we have to be careful with them when we talk about rotating reference frames. Now, unfortunately, inertial reference frames can be hard to come by. Again, inertial is non-accelerating, but we're actually sitting in a planet that's rotating, so it's spinning around on its axis. It's revolving around the sun, and that sun is actually revolving around the center of the galaxy. So there's a lot of circular motion going on in our lives. However, this only affects us in very large scales and very small ways. So the labs that we're doing in class and the experiments that we'll be looking at, those large-scale motions of the rotation of the Earth going around the sun, and so on, will not affect the results significantly of our experiments in class. Now, if we had really, really, really expensive fine precision instruments, we might be able to see a little bit of an effect, but for the most part, we can pretend that our lab frame and our classroom is an inertial reference frame. But let's look at the large scale. What do I mean by the Earth is rotating? This is not an inertial reference frame. Well, here's an example of the Earth, right? So we have the axis of the Earth, the North Pole on top, the South Pole below, and I have the dotted line representing the Earth's equator. The Earth rotates on its axis once every 24 hours. Let's pretend it doesn't. Just for a moment, let's pretend the Earth has no atmosphere and the Earth has no rotation. So let's put a cannon on the North Pole and fire it due south, a really powerful, large, imaginary cannon. So we fire that cannon due south. What should happen is that cannonball's path, if we had a powerful enough cannon, right, fire it over the horizon, it will continue due south, eventually passing the equator, and will actually hit the South Pole. Seems fairly straightforward. But the problem is the Earth is rotating. So what happens is, as the cannonball is in the air, the Earth is actually spinning, once on its axis, spinning underneath that cannonball. How fast it's spinning, again, depends on what your latitude is. On the equator, it's moving 1,000 miles an hour to, in this case, to the right. So when we look at the path of the cannonball above how the geography, where does the cannonball actually land, the path the cannonball takes actually appears curved when the Earth is rotating. This makes it look like, from our perspective on Earth, that there's an invisible force accelerating the cannon to the left, when in reality, it's the Earth spinning underneath it. This imaginary force is called the Coriolis force, the Coriolis effect. Now, even though it's a fictional force in that it actually doesn't really exist, it's a product of the Earth's rotation, it has effects. The fact that the Earth is a spinning ball and a non-inertial reference frame has real-world effects. One of those effects is hurricanes. If you've ever looked at hurricanes, right, they rotate counterclockwise in the northern hemisphere, and they rotate clockwise in the southern hemisphere. There was an old program called Mr. Wizard's World when I was a kid that talked about the Coriolis force and how it controlled bathtub drains and toilets would spin in one direction in the northern hemisphere and spin in another direction in the southern hemisphere. Well, it turns out that's not the case. A toilet is too small a body of water to really measure the Coriolis force. A large swimming pool, maybe you might be able to measure the Coriolis force. A lake, yes. An ocean, certainly. So the air, the fluid, the air that we breathe, is affected by this Coriolis force, giving us the direction that hurricanes spin, and also actually gives us our atmosphere and the effects of our atmosphere. The fact that our Earth is spinning is what causes, in the United States, the weather coming in from the west. If you ever wondered why, for Wisconsinites, right, we get a storm hits Minnesota and then it comes into Wisconsin, not the other way around. That's because of the large-scale flows of the atmosphere on the Earth caused by the Coriolis effect. So, again, this is a fictional force, but it has a real-world consequence. There is no force really pushing this to the left. It's the fact that the Earth is spinning underneath it to the right that gives it that motion.